Welcome to an example of classifications of functions such as one-one function, onto function, bijections, and invertible functions. Check the injectivity and surjectivity of the following function. F defined from z to z given by f of x is equal to x square. Here, z is the function given to us which is set of integers, all positive and negative integers. Domain as well as codomain both are in set of integers. And the rule by which the image has to be created under this f is every x will be related to its square. So the image of 4 will be 4 square, that is 16. Image of minus 3 would be minus 3 square, that is 9. This is the function given to us. We need to check whether it is a one-one function. What is one-one function? A function f defined from a to b is called one-one function or injective function if distinct elements have distinct images. That is, when we take different elements, distinct elements from the domain, their respective images should also be distinct. That is, distinct elements, squares should also be distinct. That is what the rule given to us this time. This definition can be written like this also. Whenever x1 and x2 are unequal, that should imply that their respective images under this rule f should also be unequal. Or, in other words, in case the images happen to be equal, then the pre-images should also be equal. So, whenever x1 and x2 are unequal, their images should be unequal, or in case the images happen to be equal, the pre-images should be also equal. These are the two interpretations given for this definition. So to prove this, let's go by general element method. That is, let two images be equal for some x1 and some x2 of the z, the domain, the set of integers. Let the images be equal for some numbers. Now, for it to be called one-one function, this should imply that the x1 and x2 should also be equal. Let's see whether it would happen. F of x1 equal to f of x2. That means f of x1 is x1 square, f of x2 is x2 square. So this equation means x1 square is equal to x2 square. Be careful. Don't simply take off the squares and say x1 equal to x2, which may not be true. So we go ahead simplifying this equation. x1 square minus x2 square is equal to 0. This second degree equation we can be factorized. x1 minus x2 into x1 plus x2. This product can be equal to 0 in two ways. Two cases arise. Either x1 minus x2 equal to 0 or the other factor x1 plus x2 equal to 0. Which means x1 is equal to x2 or x1 is equal to minus x2. These are two ways that these images can be equal. Now you see here, the x1 and x2, they can be of opposite sign because we have all positive and negative numbers here. So x1 is equal to minus x2 is possible because the x1 and x2 are taken from set of integers which include positive as well as negative numbers. So here it looks, when the images are equal, it is not very strictly implying that the x1 and x2 should be equal. There are other possibilities also. So when the images are equal, the pre-images may not be equal. The pre-images can follow this way also. So it goes against the definition of one-oneness. So we say f is not one-one function. This method is called general element method. We never took a numerical example to establish it. Whereas the same concept, same proof can be written using a counter example, a numerical example that goes against the definition. For that, I'm using the first interpretation. Let us take two numbers x1 and x2 which are unequal. I'm taking 2 and minus 2. Of course, 2 and minus 2 are unequal. But let's see 2 and minus 2. What will be their images? 2's image will be 2 square, that is 4, and minus 2 square also is 4. Therefore, 2 square and minus 2 square both are equal means f of minus 2 and f of 2 are equal. The images of these two unequal numbers are equal. That means two distinct elements we took here, but their images happen to be equal. Hence, this interpretation did not go correct. For unequal elements, the images did not become unequal, they became equal. So this numerical example goes against the definition of one-oneness. Hence, we can say this function is not one-one. Let's see whether this function is onto. To call this function onto function, what is the condition? A function A defined from A to B is called onto function or surjective function if for each element y that we take in the codomain, there exists at least one x in the domain such that f of x is equal to that y that we started with. Let us see these three stages in this example. I'll begin with let y an element of codomain. Let y be an element of codomain. Y is a representation. Y is a general element. Now, if possible, let that y be equal to x square. If possible. Is it possible? Yet to be checked. If possible, let that y that I have taken in here be equal to x square for some x. For some x, if that y is x square, the x should be square root of y. Now the thing is, this x that we have obtained, will it belong to the domain? Will this x belong to the domain? X, any integer, its square root. If that integer was 3, x should be root of 3. Oh, root of 3 is not an integer. Therefore, we are forced to say this root y need not belong to the domain. So, that chance that we tried, if possible, let it be so, is not going okay. It's not possible for an x that in the domain. Therefore, we could not get the second stage satisfied. Hence, we conclude that the function is not an onto function because any element that we take here, for that a corresponding x we are not able to find. This fact we can highlight through a numerical example also. Since we are showing that this function is not onto, a numerical example, a counter example is also fine. I go by a counter example. Let us take y is equal to 3. Let it belong to the codomain. Now, is there any x whose square can be this 3? That is what it should satisfy. I have taken a y in the codomain. There should exist at least one x in set A in the domain so that its image is 3. Which integer square can be 3? No integer square will be 3. So we write there is no x in the domain, for which x square could be equal to 3. This goes as a counter example. So we can conclude that the function is not an onto function.